Morning, this is your Stat Sensei, Mr. Spensei, and this is Death Packet on chi-squared and regression, problems 81 to 89. So which of the following scatter plots provides evidence that the condition of equal variance for inference for the slope of the regression line has not been met? Okay, so the way we need to look at it is, are the data points spreading out? So if I were to draw a line, it's like, no, looks like the data points are staying fairly similar. Here, there's absolutely no variation, which is crazy. Rarely happens. Here, pretty consistent. It's definitely not getting wider or narrower. When I go to here, it's like, well, I don't know what my regression line is going to be about here, I guess. We're going to have a correlation of zero, so very low correlation. And I guess I should say this has a positive correlation, a negative correlation. This also has zero correlation. All right. Because it doesn't matter what x is, y is going to be the same. So this has zero correlation. But when I look at this, what do I notice? I notice these data points are pretty close. There's not much variation. Then there's a little more variation. And then we have a whole lot more variation here. So the distances between the prediction line are changing. And because the differences between the prediction line are changing, the variances, this is the one that's failing homoscedasticity. Homoscedasticity is the call for equal variance. It's called homoscedasticity. And it didn't have to look like this. It could have looked the other way. It could have looked like a funnel where I'll draw it this way, where this is my prediction line and I have data points like this, and then data points like this, and data points like this, and data points like this, and I get closer and closer. And so once again, it's failing the variation because we're getting closer and closer. All right. I hope that helps. Best answer choice to 81 is E. All right. Moving on to 82. A scientist is interested in whether there is a linear relationship between the amount of mercury in a lake and the surface area of the lake. The scientists collected data on 22 lakes of a similar type, selected a random sample, and used the data to test the claim that there is a linear relationship. The following are their hypotheses. So they're saying there is a linear relationship or there is not. The test yielded a t-value of 2.86 with a corresponding p-value of 0.05. Which is the which of the following is the correct interpretation of the p-value? Well, first off, remember that p-value is the probability of getting a test statistic this extreme or more extreme given that the null is true. So given that there is no relationship, the probability that we get a t statistic of 2.086 is 0.05. All right. Um, if there's a linear relationship between the amount of mercury in the lake and the surface area of the lake, the probability of observing a test statistic as extreme as 2.0x6 or more extreme is 0.05. All right. The problem is this is equal. Well, remember, this is no relationship, and this is a relationship. So if our slope is zero, we have no relationship. So Um, and so it's not if there is a linear relationship, it's if there is not. So we can get rid of this one, we can get rid of that one because it says if there is. The next one, if there is not a linear relationship between the amount of mercury in a lake and the surface area, the probability of observing a test statistic of 2.086 or greater is 0.05. This is close, but I really wanted to say as extreme or more extreme because we need to talk about both directions. This is only talking about greater. I don't really like this one, so I don't think it's going to be this one. If there's not a linear relationship between the amount of mercury in the lake and the surface area of the lake, the probability of observing test statistic of 2.086 is 0.05. We have to say as extreme or more extreme or greater or less than. We have to give a direction. This is C is better than D. E, if there's not a linear relationship between the amount of mercury in a lake and the surface area of the lake, the probability of observing a test statistic as extreme or more extreme is 0.05. This one was just greater, but as extreme, that could be greater or it could be less than. And remember, we had a not equal to. So not equal to means it could be either direction. E is our best choice. This would have been our best choice if our alternative had been a greater than. Okay. So for 82, we have E. All right, 83. A baseball enthusiast carried out a simple regression, a linear regression to investigate whether there's a linear relationship between the number of runs scored by a player and the number of times the player was intentionally walked. Computer output for the regression is shown. All right. Um, Let B1 equal the slope of the regression, the slope of the population regression line used to predict the number of runs scored from the sum of the intentional walks in the population of baseball players. A t-test for a slope of the regression line was conducted for the following hypothesis. All right. So they're saying that there is no relationship and there is a relationship. What is the appropriate t statistic for the mean? Well, the formula for t statistic is t equals b over sb, which is the slope over the se of the slope. So there's my y-intercept. So this is my slope row right here. So my slope estimate is 0.5, and my standard error of the slope is 0.037. So let's divide those out. Oh, I don't have to. Turns out they gave that as an answer choice, 0.5 divided by 0.037. Had we divided it out, a lot of times they'll ask you for the t statistic. You just go 0.5 divided by 0.037. I said, oh, a t statistic of 13.51. All right, moving on to 84. A state claims that there is a linear relationship between the number of toll booths open at the same time and the revenue generated by tolls. The state collected data and used the data to test the claim that there is a linear relationship. At a significance level of 0.05, the state tested the following hypothesis. Remember, this is relationship, a linear relationship. This is no relationship. All right, the test yielded a p-value of 0.03. Which of the following is a correct conclusion about the state's claim? So, I'm sorry, I wrote that wrong. This is no relationship, and this is relationship. If it's zero, then there's no relationship. So, our p-value is 0.03. Our alpha is 0.05. We are rejecting. So we're rejecting no relationship, and we believe that there's a linear relationship uh, between the toll booths being open and time. The null hypothesis is rejected because 0.03 is less than 0.05. Liking that so far. There's plenty of evidence to suggest that there is a linear relationship between revenue and the number of toll booths. That sounds really good. The null hypothesis is not rejected. That's wrong because we rejected it. The null hypothesis is rejected because 0.03 is less than 0.05. There is not. No, there is sufficient. The null hypothesis is not. Yeah, no, it's rejected. The null hypothesis is accepted. We never accept a null. So our best answer to 84 is A. 85. A reporter was interested on the relationship between the size of a dining party and the amount of time it takes for the dining party to be seated at a restaurant. The reporter selected a random sample of dining parties from a certain region. The resulting data were used to complete a linear regression of time in minutes it takes for a party to be seated versus the number of people in the dining party. All right. So based on the residual plot, which condition for inference for the slope of the regression does not appear to be satisfied? What I notice is on the residual plot, I'm getting more and more variation. This is pretty close to the prediction line, a little further from the prediction line, and here I have big residuals, so I have lots of variation. So it appears that my variation is not staying consistent. Remember the term for variation not stay or variation staying consistent is known as homoscedasticity. This failed the homoscedasticity. All right. The sum of the residuals is equal to zero. No, that's always the case. The standard deviation of the distribution of time to be seated is the same um, for each size of the dining party. I like that. The data were collected using a random sample. No, they already said that. The sample size is no. The residuals are approximately normally distributed. We don't know that. That's not what it shows. What it shows is the standard deviation of the distribution of time is the same. And what we're looking at is the variation is not the same. So for 85, I'm looking at B as being the best answer. It's failing homoscedasticity. The variation is not the same, and it should have been the same. These all should have been equally spread out one way or the other. It should have looked something like this: boom, 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 or boom, 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 boom. Really spread out. It could be one of the two, but they need to be similar. They can't be fun. This is looks like it's spreading out. Okay. All right. Number 86. An agronom whatever is an expert in soil management and crop production. Guess what? I'm not. I'm not that. A certain state hires an agronomist to investigate whether there's a linear relationship between a wheat stalk's height and the yield of wheat. The agronomist collected data and used the data to test the claim that there is a linear relationship at a significance of 0.05. The agronomist tested the following hypothesis. All right, so this is no relation, and this is a relation. All right, the test yielded a p-value of 0.25. Which of the following is correct decision? Well, if p equals 0.25, that's greater than alpha of 0.05. So we're going to fail to reject. All right. The null hypothesis is rejected? No. The null hypothesis is not rejected because 0.25 is greater than 0.05. There is sufficient evidence? No, there is not sufficient evidence. The null hypothesis is rejected? No. The null hypothesis is not rejected because 0.25 is greater than 0.05. There is not sufficient evidence to suggest that there is a linear relationship. Yes, because we always restate the alternative. So for 86, I like D. Let's look at E real quickly. The null hypothesis, we don't accept the null. All right, that's a no-no. We don't like that word. 87. A high school basketball coach wants to see whether there is a linear relationship between player height X and the number of points scored in a game by the basketball players in the coach's state. Y. So we have X is height, Y is the state. The 96% confidence interval for the estimate uh, of the linear regression line resulted in player height to points scored in the game is calculated to be negative to this. Assume all conditions for inference for slope of the regression line were met based on the confidence interval. Which of the following claims is supported by the confidence interval? First off, zeros contained in the interval, so we can't. There does not appear to be a linear relationship. So that's the first comment I want to say. Each player scored at most. No, that's not what it meant. The average difference between actual points scored and predicted point scores is between this. Uh, no, um, that's not quite right. That's close. There's a positive linear relationship. No, because we have negative. There's a negative linear relationship. No, because we have positive. It cannot be determined whether the linear relationship between player height and number of points scored for basketball and the coach is positive or negative. That's right. All right. For 87, we like E. There does not appear to be a linear relationship because we have zero contained. 88. Which of the following would be an indication that normality condition has been met for a t-test for the slope of a regression line? A residual plot with no apparent pattern in the residuals, Okay. That's important. All right. That's certainly important. Um, but that's not what we're looking for. That just tells us whether um, a linear relationship is appropriate. So that tells us whether a linear relationship is appropriate, not whether or not it's normal. Okay, so that one I don't really like. A histogram of the residuals that is centered at zero is unimodal, modal, and symmetric. Bing, bing, bing. That's definitely true. A dot plot of the residuals that's centered at zero and strongly skewed. Strongly skewed. So that's bad. So the only choice for 88 is B. This is a true statement, but it has nothing to do with normality. It just tells us whether or not um, a linear regression model is appropriate. Okay, 89. Eliza plans on constructing a confidence interval for the slope of a regression line. She creates the residual plot shown to check the conditions for creating the interval. Which of the following conditions appear to be met based on the residual plot? All right. So when I look at this, I look at 89 and I go, you know what? Um, it, it appears that it's linear because this is random, and that's kind of what that shows. The standard deviation of y is constant for different variables of x. Yes, it looks like that because it looks there's no variation. We don't have it spreading out like this. Our dots aren't going like this, starting off close and getting far, or starting off far and getting close. So it looks like that's met. The value is zero is contained in the confidence interval. That is not a condition. All right, that's not a condition. So our best answer for this is D, which is 1 and 2. All right. I hope this helps, and I certainly look forward to seeing you on the next one. Thank you.